Alright, in this video we're going to talk about Unit 3, Objective 2, Antiderivatives of Basic Functions. So just like many other things in math, the derivatives that we've just been taking in the last unit are going to have an inverse function, and those things are just going to be called antiderivatives. So it's going to be the opposite, the anti of the derivative. However, we're not going to have as many rules for these antiderivatives as we did for derivatives. So while I said that the derivatives have the inverse function of the antiderivative, we're not going to be able to take the derivative of the antiderivative of every single thing that we see. Some things that we're not going to have rules for. We're not going to have rules for products, quotients, or chains. And that's yet. This yet can really, it's going for all three. So we will get a product rule eventually. We will get a quotient rule eventually. We will get a chain rule eventually. But for right now, the only thing that we can do is power rule and chain rule. So if we have a product, a quotient, power rule and trig rules. So if we have a product rule or a quotient rule or a chain rule, we're going to have to try to get rid of those things. So our power rule for antiderivatives, so the antiderivative of x to the n dx, is going to be the exact opposite of what we did before. So before, we decreased this exponent by 1, and then we multiplied by our exponent. So in this case, we're actually going to increase our exponent by 1. And instead of multiplying, we're going to divide by that, or multiply by 1 over our new exponent. Then we're also going to have to put this little plus c thing over there. And c is just a constant. And the reason we need that is because we're saying if I take the derivative of this function here, I'm going to end up right here. So if we take n plus 1, drop it down front, multiply, we have n plus 1 over n plus 1, going to give us 1. Decrease this by 1, so n plus 1 minus 1 is just n. So we're going to get x to the n. But this really could be any function, right? We could have x to the n plus 1 plus 4, if this were a 4, right? Because the derivative of 4 is going to be 0, so we're still going to end up here. It could be 12, it could be 1,000,000, it could be 42, it could be anything. So we're just going to say it could be any constant at all. So we have to put this plus c for our antiderivative. So the antiderivative, again, we kind of want to think about it as the derivative, or what function has a derivative of this thing right here. So what function is going to have a derivative of x to the n, and it really could be infinitely many things because of this c. Now, if you have a product, we can turn it into a power rule by multiplying a lot of times. And that's going to work the same way with derivatives. We can get rid of a lot of power or product rule problems for derivatives just by multiplying things out. If we have a quotient, we can turn them into a power rule by getting rid of STDs a lot of times. If we don't have an STD, then we can't do it on this problem. All right, we're not going to, if we can't get rid of our quotient completely, then we can't antidifferentiate yet. Same thing, it's going to work with as products with our chain. If you have something like x plus 4 raised to the 5th power, if you wanted to multiply it out 5 times, then you'll have power rule. We're also going to have some trig rules, and the trig rules are going to work the exact opposite of what they did before. So again, we need to think what function has a derivative of sine. So the function that's going to give me a derivative of sine is actually negative cosine of x. Right? If I take the derivative of cosine, it's negative sine. So the derivative of negative cosine is going to be negative sine, giving us positive sine. The antiderivative of cosine, so what function has a derivative of cosine? Well, sine has a derivative of cosine. What function has a derivative of secant squared? That's going to be tangent. And all of these things have our plus c. What function is going to have a derivative of cosecant cotangent? That's going to be negative cosecant x plus c. Secant tangent's just going to be secant x plus c. And cotangent squared is going to be negative cotangent. Oops, that's a mistake. This should be cosecant. Antiderivative of cosecant squared of x dx. And that's going to be cotangent of x plus c. Now notice we're using x's here, we're not using the u's. If we had something like the antiderivative of cosine of x plus 4, we can't do that problem because that's a chain rule and we don't know how to deal with chain rule yet. So, just need to know your rules. It's more things to memorize. When we were doing our derivative rules, we kind of took a look at this little unit circle and we said that sine is going to be positive here, cosine is going to be positive here, sine is going to be negative down here, cosine is going to be negative over here. And we said as we go clockwise around the circle, we're taking derivatives. So that way would be our derivatives. It actually is going to work out that if you go counterclockwise around your circle, you're taking antiderivatives. So if you think sine starts here, it's antiderivatives negative cosine, we have the rule right here. So clockwise is going to give you derivatives, counterclockwise is going to give you your antiderivatives. So let's look at a couple of examples on our antiderivatives. So looking at number 1, we have a quotient, something over something, so we can't deal with it the way it's written, so we need to get rid of our STDs. Remember, STDs are single term denominators. That's going to allow us to split this up into 2 separate pieces. So it's really uncombining our like terms, right? Usually we need to get a common denominator so we can add 2 fractions together. This time we're going to take 2 fractions apart. And then we're going to simplify, because this is still a quotient. We still don't have a quotient rule. So x to the 1/3 divided by x to the 2/3, so that's subtract our powers, that's going to be x to the negative 1/3. And this is a quotient, right? We have the x in the bottom, we can't have that. So we need to bring the x to the top and just make it a negative 2/3 power. So long as it's a power, we can deal with it. It can be negative and that's going to be fine. So our rule for our power rule is increase our exponent by 1. So our exponent is going to be 2/3. And then divide by your new exponent. So we need to divide by 2/3, which is really just going to be multiplying by 3/2. Increase your power by 1, that's going to be 1/3. Divide by 1/3, which is really going to be multiplying by 3. So we're going to get a 9 there, and don't forget your plus c. So if you take the derivative of this, you're going to end up here, which could be here, which would be here. So if you went and simplified, you'd end up right here if you took the derivative of this problem here. So that's how we're going to deal with STDs. Trig rules, remember, we only have a certain amount of things, and cosine divided by sine, that's a quotient. We can't deal with quotients, so we have to find a way around it. So what we want to think about this is as 4 cosine of x divided by sine of x times 1 over sine of x dx. And what that's going to allow us to do is cosine over sine is cotangent. 1 over sine is cosecant. And that's a rule that we should know. So we can use this 4. This 4 is just multiplied by all this stuff, so we can really think of that as being outside. So we have cotangent, cosecant, which could really be cosecant, cotangent. So if we look at our rule from the previous slide, the antiderivative of cosecant, cotangent is negative cosecant of x plus c. And then we have to multiply by that 4 that we pulled out front. So we're going to say negative 4 cosecant of x. And then we're still going to call this plus c. because c is a constant. So if I take a constant and I multiply it by 4, I still have a constant. So we're just going to call it c. So negative 4 cosecant x plus c. So that's going to do it in this video. We'll see you in the next one.